we're going to prove the following important theorem on row spaces. So say we have two matrices, matrix A and matrix B. And suppose matrix B was obtained from matrix A by applying one elementary row operation to A. Okay? Now, in that case, the row space of the two matrices is actually the same. The span of the rows in B will be the same as the span of the row vectors in A. Okay? All right, so to do this, we need to consider each elementary row operation individually. There are three elementary row operations. Okay? We can swap two rows. We can take a non-zero multiple of one row and exchange our original row with that non-zero multiple. Okay? Or we could add a multiple of one row to another row, and that's our new row. All right? We will consider just the first two. The third one, you will get the idea. It's going to be much the same process. Okay? So let's start with, let's let R1 to Rm be the rows of A. So matrix A, R1 is the first row, R2 is the second row, and so on. Okay? Now, as we notice, there are three elementary row operations, so let's consider the first one first. What if we swap rows? So clearly switching the order of the vectors in the span will not affect the span. Okay? Remember, the span is just the set of all linear combinations of that spanning set of vectors. So if I take this vector and swap it with that vector, okay, or take this row and swap it with this row, all the rows are still there. All the vectors are still there. So I'm taking a linear combination of the same vectors. I'm just changing which one comes first. But it's still all linear combinations of the same set of vectors. So the span won't be effective. So the row space will stay the same, right? Because it's the span of the same set of vectors. And the row space is just the span of all of the row vectors in the matrix. Okay. So now suppose B was obtained from A with a different elementary row operation. That is by multiplying one of the rows, let's say the ith row of matrix A, by a non-zero constant K. Okay? So in this case, if this is A, then in this case, B would be the same matrix, but somewhere down here, instead of the ith row, now we have K times the ith row. Okay? And so now, this would be the row space of A. It's the span of the original rows of matrix A. And this span here is the row space of B. It's the span of the new rows of the new matrix after the row operation. You could tell because we've multiplied row I by K. So if I could show these two are equal, then I'm done. Okay? So to do this, it's kind of a two-step process. One, we need to assume that if we have any vector in this set, in the row space of B, then it is also in the row space of A. Okay? But also we need to show that for any vector in the row space of A, that vector is also in the row space of B. Okay? So every vector that one of the row spaces has, the other row space also has. All right? So let's start with the first direction. Let's say V is in this span of vectors, and remember this is going to be the row space of B because it's after the row operation has happened. All right? Because V is in the span, we could express V as a linear combination of the vectors. Okay, some constant times R1 plus some constant times R2. And then when we get to Ri, we just use the row after we've done the operation to it. So some constant times KRI, all the way until we get to some constant times RM. Okay, but then if we just change where the parentheses are, and we can do that by associativity, then this is just a linear combination of the rows R1, R2, all the way to RM, right? This is a linear combination where we're taking Ri before we have done the row operation. Ai times k is just a constant, which means because I can express V as a linear combination of the rows of matrix A, R1, R2, Ri, Rm, just a constant times a vector, V is also in the span R1 to Rm. Okay? And so what that shows is that everything in row B, in the row space of B, is also in the row space of A. And so the row space of B is a subset of the row space of A. Everything in this set is also in this set. What we need to show is that the reverse is also true now. Okay? So now take a different vector W, a potentially different vector W, in the row space of A, in the span of the rows of A. Row space of A. Because it's in the span, we can express W as a linear combination of the rows of matrix A. So a constant times the first row, plus a constant times the second row, plus a constant times the ith row, all the way to a final constant times the last row of A. Okay? Now, remember, k isn't 0. The elementary row operation here, multiply a row by a constant, that constant has to be non-zero. All right? Because it's not 0, that means we could divide it. So what we're doing here is we're saying, oh, okay, well, instead of multiplying Ri by Bi, B sub I, that constant, is equal to B sub I over K times K. Right? Clearly they're equal. I could cancel the K's and get this back. But what I want to do is I want to take this K and sneak it up right next to Ri. Okay, do you see that? And so now don't have a constant times the ith row here. I have a constant times K times the ith row. Okay, this is now the ith row of matrix B. This is the linear combination after I've done the row operation. And so now I have a constant times row 1 plus a constant times row 2 plus a constant times the ith row of matrix B after we've done that elementary row operation. I've multiplied row I by K. And I still have just a constant times the vector after the elementary row operation. Okay? And so W can be expressed as a linear combination of these vectors. Okay? Which means that W is in the row space of B. So now I've shown that any vector in the row space of A is also in the row space of B. So that means that the row space of A is also a subset of the row space of B. Anything in the row space of A, any vector in the row space of A is also a vector in the row space of B. It can be represented as a linear combination of the rows of B. Okay? Well, if B is row space of B is a subset of the row space of A, and row space of A is a subset of the row space of B, then that means that, put those together, row space of A and the row space of B have to be equal. Which is what we wanted to show, right? So we talked about this elementary row operation, swapping two rows. The row spaces were equal. We talked about multiplying a row by a non-zero constant, and we saw that the row spaces were equal there. The argument for this last elementary row operation is very similar, so we're not going to cover it. but it also holds. Okay, so if we perform an elementary row operation on a matrix, the row space before the elementary row operation and the row space after the elementary row operation are the same. Okay, we get a couple corollaries from this. Here's our first corollary. Now remember, a corollary is just a quick result that follows pretty much immediately from the preceding theorem. Okay, so it comes after a theorem, but it's little and is more consequence of the theorem. Okay, so here we were talking about one elementary row operation, but notice I could string them together then. If I apply another row operation to get another matrix C, well, that would be equal to the row space of matrix A, or I'm sorry, matrix B should be equal to the row space of matrix A. So it's not going to hold for just one elementary row operation, but any number of elementary row operations. So now, if I obtain matrix B from matrix A by applying potentially multiple elementary row operations, then the row spaces of the two matrices will be the same. Okay? And in particular, we have our last corollary here. The row space of A is equal to the row space of the reduced row echelon form of A. And that's because we get the reduced row echelon form of A by just applying many elementary row operations to matrix A. And so since this is just something we obtain from A by applying elementary row operations, their row spaces are the same. This is useful because once we have a matrix in reduced row echelon form, it is really easy to identify a basis for that, the row space of that matrix. Okay? It is easy to find a basis for the row space of a matrix in reduced row echelon form. Okay, so generally that means if we want to find the basis for a row space, we will generally take the matrix and transform it into its reduced row echelon form. And from there, we can easily identify a basis for the row space.